is speaking on subject insight into irreversibility and entropy from turbulence perspective.
All right, thank you, and thanks for organizers for organizing this nice meeting. So I will, after lunch, I don't want to strain you, so there won't be any equation really, just a story type. So these are the papers which I wrote in the last couple of years. So this is a part which is, which in fact the question came in the last talk I gave on Tuesday here only. So, so I'm talking about time reversal symmetry breaking or irreversibility, but we can apply similar idea on parity as well. So my point is that there are some stuff which is based on environment, not necessarily, not too dependent on the details. So this is a tree, Amalthus tree, and if you look at the fruit cells, they twist in both right helical and left helical. Okay. Now, why is it so? You can make models. You know, in fact, during the talk there were some suggestions that it is genetic. Well, it is not connected to genetics. It is just a drying up of the inner surface and in the environment. Okay, so in fact, there's a tree right there in front of the guest house. So I found all this stuff. It was just there. So in fact, if you look at this, when the seeds are out, then the two parts of the fruit just opens up, and both of them turn in different directions. And that's how I have in my bag pretty nice those stuff. If you can easily see that they are indeed those shells. Okay, I mean this is pretty nice helical shell. Okay, so what is the origin? I mean I can make models, I can use genetics, but you don't need to actually. You can just say it's drying up. Of course, there is some interesting physics which I'm not thought about them. I won't think about them, but it is because of the environment. So we can also apply similar idea to time reversal symmetry. So this is a fourth talk on arrow of time. So I don't need to say this, except that the fundamental laws of physics, except weak nuclear, they are symmetric under T to minus T. That means if at a fundamental level, if I see a phenomena going forward in time, if I reverse by changing the velocity, I get back the same trajectory. Okay. It turns out in that paper, the time reversal is pretty. I mean, I won't say bad symmetry, but it's a very difficult kind of symmetry to operate on. So, for example, people say, no, reverse the whole universe. I mean, you can't reverse the whole universe. It's nonsense. Okay. So we should not reversing the whole universe or biology. Why I am not getting younger? Just imagine reversing the intake of oxygen into intake of CO2. So some of these things are impractical, and we need to invoke environment, okay, to answer those questions. So I work in turbulence, so there entropy does become a problem, which I'm going to speak a bit on in the last slide. So for me, one nice idea, irrespective of entropy, we don't need to invoke entropy. Entropy is not very well defined for turbulence. Okay, I mean, I assure you, you can just look at the literature. Entropy is pretty much the usual entropy. Bose entropy is not well defined. So what I suggest is that we can use the energy transfer. So this is again a typical thing. You force a system at large scales, and it's not only turbulence. Like Earth is driven by the sun. Biological systems are driven by the surrounding. You know, the ocean is feeding the life in the ocean. So it is driven by a large scale, and typically there is dissipation at small scale. It is not for all systems, but in 3D, this seems to be a pretty generic picture. And with that, this energy cascade, if you have some big source and big sink here, and there's a cascade. And this cascade is generic. So I can use it to define arrow of time. In fact, I can make it slightly more quantitative. So this is the only math part, okay, in my slide. There's nothing extraordinary. This is Kolmogorov theory. So we have velocity field at two different points. There are points r and r plus l. Take the difference and dot product with L itself and cube it, okay. So this quantity proven by Kolmogorov is minus 4/5 epsilon r. Now please remember the operation u goes to minus u. Time reversal symmetry requires that I need to change the velocity. Here I can do it. In turbulent flows, experiments may be difficult to reverse all the velocities, but in computer I can do it. Okay, if I reverse the velocity for that particular frame, what's going to happen? U goes to minus, u goes to u prime, which is minus u. So what's going to happen to this object? It's odd in delta u. So it's going to change sign, and here it is negative, right? Epsilon u is negative, positive, r is positive, the negative sign. This quantity must be negative. It's a law of nature. Okay, so in the reversed movie, which is a fake movie, I'll find this to be positive, and that's how I can say that this is a fake movie. And I can say that I can distinguish between the real experiment and the fake experiment, which is performed by reversing the velocity. So like trajectory, projectile I saw was going forward, and reverse projectile was equal, well, possible. But here in turbulence, a reverse trajectory is not real, because there is a dissipation at small scale, and we see if I force something at large scale and dissipate small scale, it is not symmetric in time, at t2 minus t. So that is what is breaking the time symmetry in real life. That's one feature. We can evoke more. So entropy is one which I'm very fond of, by the way. I'm not criticizing Boltzmann or Gibbs. It's a fundamental work they did, but that works for thermodynamics, like for air conditioning, that principle works, and we are all benefit from it, but that's not all. And here in turbulence, we have this, but there are more. So open systems like combustion. Combustion, I'm not going to apply Kolmogorov theory. Okay, Kolmogorov theory is too mathematical, and combustion. So combustion, what happens when I take CO2 and mix oxygen, spark, and boom, it creates light, sound, and I'm not going to bring that light or sound. So in any open system, it is impossible to reverse it. And most of the world, we find open systems, right? I mean, the earth is an open system. So this is not going to reverse. I mean, that is, we can be assured that, and also bad thing that I can't grow younger. It's just that it's not possible. Also, one thing which is not talked about, which is not, I mean, you can't, I mean, there are people who try to define causality from math, but I think causality is a basic principle. If you look at old books, I mean, old books means what Newton wrote, or even Einstein, they all believed in causality. A causes B, so A will be before B. Okay. Now, in real life, so the cause and effect will the time-reduced symmetry breaking. Now, last, I'm just going to talk a little bit about entropy, because I think this idea came in a lot of talks. So I have 2 minutes, 2-3 minutes. 30 seconds. Okay, so let's quickly go. 30 minutes was blessing. Anyway, so let's look at conduction. Okay, so this is I have ideal gas. I heat from the bottom and cool from the top, but it's conduction. So an ideal gas. Okay, so I'll apply this Boltzmann formula. Great, it works, and we can get entropy. But what if I increase the temperature difference and I get convection? Now here I just increase the temperature difference by maybe 1 degree. From, let's say, this difference was maybe 20 degrees and this 21 degrees. So the temperature difference is not much, is only 1% or not even a percent. But this is more ordered. You'll agree with that. No? This is more ordered. Then how do we define this order out here? This is non-equilibrium, and how do I define it? So the idea which is here is that I can take the Fourier transform of this flow, and I can get Ek divided by total energy as Pk and minus Pk log Pk. It's a multiscale entropy. This is not same as Shannon entropy. Shannon is at a given scale, but it is talking about order at different scales. So it's a multiscale entropy, and it works quite nicely. In 3D, it turns out that you go from here to there, and we can apply this formula, and this entropy increases. But it turns out for Euler, thermodynamic entropy is constant. You believe me, it is constant because there is no viscosity. Now, actually, but I did learn from this workshop that there is some new entropy for depending on paths, which I need to think about. In 2D, it turns out this entropy decreases because the system gets ordered, and this SH, and in fact, is decreasing with time. So system can get more ordered, but it's not a thermodynamic order, it's a hydrodynamic order. For example, the universe, there are places where it is getting more ordered. And it's possible. I mean, we can have order in isolated system. By the way, please keep in mind, Euler is an isolated system. It can get more order. So Boltzmann is for thermodynamic order, but this order is possible. This is there in simulations, but in quantum turbulence, some of this stuff, there are some indications, but I think this is something interesting to observe. So I'll end here and I can take questions.
It's time for question. 1 or 2 questions because of time limit.
Okay, good. No questions. Yeah, here.
So what about active matter systems where the energy flow is in the opposite direction?
Okay, great question. So in some systems, like in 2D turbulence, the natural cascade is backward. So the arrow of time will be positive if the flux is going back. So in the fake movie, the energy will be going forward, and I can say this is a fake movie because energy is going forward. Is that okay? Yeah. Thank you. Yeah, he has a question. Maybe it's okay.
So I want to ask that there are systems in which the system get ordered and the entropy of the universe or the environment increases. So in this isolated system, how is this law satisfied? So
those statements are made for Boltzmann order in thermodynamic order. This is true. For example, let me just give another example: gravitating systems. Okay, there are places where gravitating system will collapse to a star, right, or a planet. Is it getting more ordered or less ordered? Planet is more ordered, no? More ordered. It's isolated system.
Yes.
So I think some of it we had to. I mean, thermodynamics second law is for Boltzmann entropy. It's not for this kind of entropy. That's my way out, and needs a thought. But I think we should not believe that order will always increase, even for isolated system. That's my perspective right now. Yes.
Yes, I missed it, I think, but how is this? It was just log P log P, right? The entropy.
Yes, yeah.
So how is it different from the usual Gibbs kind of entropy or this?
Okay, so for Ising spin, P's will be P of 1 and P of minus.
It could be any distribution with any parameter.
Okay, but Shannon, if you look at the alphabets, the probability of alphabets, the probability of at a given length scale.
I can use it for ideal gas also.
Yeah, but these are single state systems. When you compute probability, Boltzmann entropy for text, it is alphabets what you're doing. If you want to apply Boltzmann, Shannon, they say, I want to get entropy of the words or paragraph. Then you need to do the Fourier transform of the text. You get my point? So I'm doing Fourier transform to get what is ordered in the text, in a paragraph, or in the book or set of books. So
the question was, it's very nice, of course, but the question was that I can use any parameter for the distribution in that formula, right?
Typically in statistical physics, without phase transition is a thing, you talk about single scale. At least thermodynamics is single scale. So these are multiscale. That's I want to emphasize the difference. Okay, thanks.
Professor.